Today, I want to talk about performance, but more from a networking angle using the new HTTP 3 protocol. So this is going to be a talk about how you could speed up your startup performance using HTTP 3. So the session is going to be broken into like 5 sections. So I'll do like an intro, do like an analysis of what is in a HTTP request, show you like a comparison of the 2 protocols, and then get into the practicalities of adopting it. I'm going to go full stack on this, backend iOS, Android, and then I'm going to share with you some of the impacts we see from adopting H3 and Coronet, which is, I'm going to explain what Coronet is. Maybe it's not that popular. Okay, without further ado, straight to the intro. First of all, about myself, I'm Elvis Chidera. I'm a staff software engineer at DeliveryHero. I've spent lots of time on like networking stuff. Like in the past, I previously worked for a non-profit in Kenya where we tried to build like an offline peer-to-peer network where people could like stay connected without actually using the internet. So having like a way to like share information between each other. And then I also worked on a project in the Middle East where we tried to like avoid like censorship on creating like a protocol for that. But yeah, all in all, I'm kind of like, I love networking a lot, but I'm an Android engineer at DeliveryHero. And yeah, enough about me. We could go, I wanted to do like a quick, why does performance matter? I guess it's obvious, but maybe at the stating the obvious. So performance, it's not just like a technical thing, it's a feature because repeatedly studies have shown like a correlation between startup performance and the business bottom line performance. We're talking about user retention, user engagement, and conversion rates, right? So here are like some excerpts from like some studies, or like also some from the developer Android website. Before going into this, I want to do like also like some primer on like network performance. So when it comes to network performance, there are 2 key things that affect the performance of networking. So the first one is latency, which is the time from when I have a data, I send it, and then the receiver is receiving it. So it includes everything from like propagation delay, which is like how long it takes the signal to transmit in the medium, to like transmission delay, which is how long it takes for me to send all that packets into the wire. And then it's also things like queuing time. If, for example, lots of people are using like a link and then the intermittent links need to like queue that. That also adds additional time to the latency. And you have even more stuff like processing time. I mean, processing time is usually fast because most of that happens in the hardware level, but it also still adds time, and especially when you have like a long route from sender to receiver. So it's like, it's the time to when my message is received by the receiver. And then bandwidth is like the maximum throughput, the maximum I could send into like a link or into like a pipe. So to use the pipe analogy, I could, for example, say, I could have a very big pipe, but if I take that pipe and I send it all the way to Australia and then back to Frankfurt, it doesn't really matter that I have a big pipe. It's going to take a long time because I have to go all the way to Australia and then to Frankfurt, compared to maybe a smaller pipe that just goes all the way from Berlin to Frankfurt. So I'll be able to like send my data, especially like a typical web request, faster if I have like a shorter latency to shorter distance between the sender and the receiver. So these are like 2 key things that play a significant role in networking performance. And when it comes to mobile, you have wireless devices, which introduce a whole suite of other problems and latency. So here's like a rough table that shows like the performance for 3 generations of wireless technology. So a good rule of thumb is to pick a data rate that is closer to the minimum and a latency that's closer to the maximum that's promised by that generation, because it's very variable, right? So you have also the generation is not a technology, it's more like a standard or specification, right? So, and it only defines or it only specifies a limited part of the entire time your request spends on the network. So you have so in this diagram here, I show like just a roughly what making a request entails on a device. So let's say your device is idle and you're starting it with a request. Most likely the device radio is in sleep mode. So 4G, for example, specifies that the time it takes to do the negotiation with something called the radio resource controller should be a maximum of 100 milliseconds. So it's like your device is in idle mode, consuming like very limited power, listening to like maybe specific things, and now we want to send. So it's going to tell this radio resource controller, I want to send. And then this controller is what tells your device to like move from idle state into like a more active state, right? So that for 4G case takes like 100 milliseconds max, whereas with the older technologies, you could see it takes a lot more time. So you have that, and then you have the user plane one-way latency, which is the time from when I have something on my device to when it arrives at the tower, the cell tower. So that 4G also specifies that it should be less than like 5 milliseconds. So all in all, 4G is quite good. So like the time from when this 4G specifies only these 2 sections that you see. The remaining other sections are not part of the 4G specification. So it's not uncommon for you to have like 4G that is quite slow because maybe the other parts are not as optimized as this initial part, for example. So pretty much what I'm saying is that like the technology, the 4G or like the wireless specification doesn't tell you much about the performance of the network. And there's another variable in the equation, which is the user equipment category, right? So say for example, HSPA, high speed packet access, a 3G Tech specifies over 36 possible user equipment category, and each category has its own performance characteristics. So this is something where you can't really say much by just saying a device supports 4G. You have to like, what equipment category is it part of? Which a more useful thing is to like try to do like a continuous estimate of the data rate and the latency that you're currently seeing. So yeah, that is I guess all the foundation you need for the following parts of the talk. So moving on to what is in a HTTP request. So making a request is simple. You specify like a URL, you specify a header, specify like a body or something, and then you just make the request and wait for like a success or failure, right? It's pretty straightforward, 5-10 lines of code. But what actually happens for that request to be serviced is not so simple. A bunch of steps is involved, and this diagram tries to like show like at a high level what are the key steps in this. It's a bit involved, but I'm going to go through it like one at a time. So the first thing you do is like, oh, I want to make a request, and if you're making an async request, like here, what is going to first happen is the request will be enqueued on in the thread queue. So if you're using OkHttp, you have like 5 max requests per host, 64 concurrent requests total, and no prioritization in the request. So like pretty much every request has the same priority. So if you start like, I don't know, 100, each one has, there's no prioritization between that. I'm going to come back to this because that presents like some problem, the no prioritization part. The scepter part, not much to be done here, just like maybe have less interceptors or make them as fast as possible, but you just like interceptors, for those who are not familiar, is something that could modify the request before it gets sent. The DNS part, usually straightforward-ish. So it's like, is there like some DNS record cached? If there is, just move forward, otherwise try to resolve it. If it involves one round trip, but this is usually fast because this just speaks to like something in your ISP usually. So this is typically fast. Then the next step in the timeline is making the TCP and TLS connection. So I'm looking at both of them together. So this takes 2 round trips when using TLS 1.3 and TCP. So a connection usually entails this. So the client is ready. I want to send a request, and it sends like a packet to the server, and the server, and then this will take like as long as it takes to propagate, and the delay it takes to like get to the server, and the server receives it, and the server acknowledge and also like says does the TCP sync ACK and sends a response back to the client. And now the TCP connection is established, taking like 1 round trip. So in this example here, like 1 trip to the server is 34 ms, a trip back is another 34 ms. So that's a simplification, obviously, but that helps us get like a rough understanding of what happens when you try to establish a connection. So TCP is done. Now you need to establish the TLS connection. So again, similar thing has to happen. With TLS 1.2, sometimes it could take 2 round trips, but with TLS 1.3, which most apps should be using today, this is usually 1 round trip. So you do like the client hello and key share, and server responds back. So 2 round trips now. So and now only when these 2 things are done can you start sending the application data. So in this example of like a round trip being 68 milliseconds, you could see that the time before your request is actually sent is like 136 milliseconds before the actual thing you want to send is actually put on the wire. All right. There's another problem, or there's one problem here where you could unintentionally introduce 1 more round trip. It's something called the initial congestion window. So typically, there's no orchestration between like the requests you make on App Startup. So you make like 5, 10, as many requests. You're fetching configs, making analytics, assets, and all of that. But then there's like maybe 1 or 2 requests that's actually necessary for you to render what is on the screen, right? So what happens is that once the connection is established, you could send all of these requests almost at the same time, right? And then your server receives it, processes it, and then when it's trying to send a response back, it's especially at the start of the TCP connection, this thing called initial congestion window, which is set to 10 segments at the moment. I think RFC 7920 or something in 2013 made it 10. It used to be 1, then it went to 3, and then to 10. So what this does is it places a limit on how much the server could initially send to you before it has to wait and say, I need an acknowledgement to proceed further. So what happens is this is 10, and taking like a max segment size of like 1,460 bytes, you get about 14 kilobytes, right? That could be sent before the server is like, wait, I'm going to wait for like a acknowledgement from the client. So this poses a performance problem because now the server has to wait, even though it might be able to send more requests. So it has to wait for its message to be received by the client, and the client to say, I acknowledge it. So you've unintentionally added 1 more round trip for your critical resource that you want to send, because we have like things like configs and analytics also being fetched at the same time. So this is like one easy problem to have. Yeah. And going back to the flow, the last thing is sending the data and downloading the data. Nothing much to speak about here, so I'll just go over those. One tip here is if you can, try to prefetch data. So usually what happens is you have like app start, you show a splash screen, you initialize app dependency, and then you show your main screen, and then you start making the request, right? That is like more logical flow. I mean, it's simple, but the most optimal thing is to put your request on the wire as soon as possible. So you want to like parallelize the timeline of like local work and remote work, such that the slowest of the two is what the user ends up experiencing as their latency, right? So if, for example, you have like some file you need to read from or some heavy initialization you need to do, figure out how to like start whatever network requests you want to do as early as possible, and then start doing those instead of like having those happen in sequence. Try to parallelize them as much as possible, because it allows things like this initial congestion window and this TCP connection to be established while you're doing other things in the app. Cool. So now to the main part of the presentation. So it's like HTTP2 versus HTTP3. It's a mouthful to say HTTP2 and HTTP3 a lot, so I'm just gonna like abbreviate them and say H2 and H3. English is not my first language, so but yeah, yeah. So so we have what is the differences between these protocols, and so H3 is based on QUIC, which is like something built by Google in like 2014, and then eventually became like a standard and became H3. But H3 is based on it, and it replaces parts of TCP, and it's built on UDP. So like when you're sending like data on the internet, you pretty much have two options, UDP or TCP. So if you try to like make modifications to TCP, it's hard because you have to like go modify all the network boxes out there, which is like, it had been tried before and it didn't succeed. Or it didn't get as much adoption. So the guys designing this were like, okay, let's use UDP and build like things that TCP provides on top of UDP. So like things like reliable stream and ordered stream of data. So this is what it looks like. And then one other thing is that QUIC has the secure layer built in, so it's not like a separate layer. And I'm going to come to why this is important, because it has like a performance impact having the TLS built into QUIC. Three key performance improvements that HTTP3 or H3 provides over H2. The first one is it provides like faster connection establishment. So the previous connection diagram I shared earlier, you see that like it requires 2 round trips to establish a H2 and a TLS 1.3 connection. With H3, because TLS and QUIC both combined, you could have just one handshake, completely eliminating one extra round trip. So imagine you're like in a emerging markets where like it's not uncommon to have like round trip times of 300, 400, or 500 milliseconds. You've eliminated like half a second just by changing protocols, and your request could start earlier. And there's one other thing, is that H3 also supports true zero round trip connection establishment. So if you've established a connection before, the server could send like some session ticket, and the client could store that, which next time the client is making a request, it just like sends that and then starts sending the data. This is called like early data. So this will allow you to not have any of this connection cost for returning users. So the second benefit of H3 is it eliminates head of line blocking completely. So H2 fixed head of line blocking at the HTTP layer. And but it doesn't fix it at the TCP layer because TCP expects an ordered byte of stream. It doesn't know about what is happening at the HTTP level because H2 tries to like multiplex or like have multiple requests on a single TCP connection. But from the TCP point, it still sees like just byte. So it doesn't know what is a request. So what happens, or what this diagram shows here is that like if, for example, I lose packet A, everything that's sharing that connection is going to wait either for the retransmission of that packet or for that packet to arrive. So again, if we're going back, if you go back to the example, if I'm making like a config request and I'm making my critical request, what this will mean is that like my config request has an issue, like a packet is lost. My critical response would be blocked until there's a retransmission of a config or like something that's unimportant before it proceeds. So, but with H3, it completely eliminates this head of line blocking problem by using a different transport protocol. And only the stream that is blocked, only one stream is blocked for retransmission of packets. And because of this, you could observe that like H2 performance, sometimes in poor connectivity situations, it performs worse than H1 because with H1 you have like multiple connections and then you could have like actual parallel exchanges happening, whereas with H2 everything just gets blocked if there's like high packet loss environment. And the final thing is H3 supports something called connection migration. So the typical problem of, or you're walking into your apartment and it's switching from like your mobile data to Wi-Fi, and then you notice like some lag, maybe the video is lags for like a few seconds or something doesn't connect while you're making that transition. Usually what happens is when you switch from like Wi-Fi to mobile or vice versa, your IP changes and TCP connections are identified by like a default tuple, IP address, your IP address, port, blah, blah, blah. Whereas with QUIC, you could have a connection ID and then you migrate that connection ID, even though like you've changed from Wi-Fi to 4G or 4G to Wi-Fi or 3G or whatever. So this allows you to like migrate your connection, and the only thing that needs to run is just like path validation. You don't need to like establish a new connection just to continue making that request. So it's called like the parking lot problem, but it's just like a problem that you run into a lot because people are like moving. They go from like Wi-Fi to mobile, and when your users, when that happens for your users, you see this huge latency spike. Okay, so now I guess what I've said so far is a lot of theory. This will be a bit more, there'll be more code in this part of the presentation. This is about adopting H3 for your apps. The first part is adopting it on the server. So this is actually the easy part. A typical misconception is, or like direction people want to try is to like enable H3 all the way to their origin servers, but this is not necessary because the benefit of H3 and H2 is primarily for the last mile. It's like your users to the edge server. It's from your edge server to origin, you could continue using H1 because these providers have they have a long-lived TCP connection to your server, and they have like good interconnects between, if they're doing their job right, they should have good interconnects between them and whatever you use in AWS or Google Cloud. So there isn't that much of the problem that H2 and H3 tries to solve in this environment. Of course, it's still nice to do like an upgrade to that, but that is, the main advantage comes from the end user to your edge. This is where you want to like upgrade to H3. For the middle mile or the first mile, there are things like Argo Smart routing and stuff like that that's going to help that situation. So yeah, usually adopting H3 on the edge is simple. Like Cloudflare has like a button, same with Fastly, and I guess with the other providers, you just like press the button and it's done. So it's really that straightforward. And on iOS, the good news is it is supported since 2021 on iOS 15. So there's really nothing you need to do besides just enabling it on your backend, and then the clients are going to like discover that your client, your server supports it. But on Android, of course, it can't be that easy. It has to be hard otherwise. So there are two options, either using Cronut or Envoy Mobile. But underneath, they both use Quiche. I'm not pronouncing that right, but Quiche. So Google Quiche. So we chose Cronut because it supports H3, which is what we want. It has request prioritization, broadly compression, and blah, 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 other stuff. And it is popular. It's used by Chrome, Google Maps, YouTube, and billions of people. So billions of people use those apps. So we're sure that like it has been battle tested. Usually most apps use OkHttp. So Cronut is kind of like recent, and from Android API 33 or so, there's a new API that's called HTTP Engine, and this underneath is based on Cronut. I mean, API 33 is quite new, so that is not the minimum version for most apps. So you're kind of stuck to like use something else. So if you're using OkHTP like us, most likely, there is a bridge that allows you to still use like OkHttp APIs while using Cronut underneath. So it's called like Cronut Transport for OkHTP, and it allows you to use Cronut without having to like completely refactor your code base. But the problem is, it hasn't been maintained last year, and it has like 18 issues. So that is not a problem by itself, but like when an issue is created and the maintainer is tagged, it's like, oh, I don't work at Google anymore. So it's like, that is your problem now. So we decided to build, because we tried this, and then we saw like we ran into like some issues, mostly performance, and then we decided to like try to build our own. How hard can it be? It was hard. The problem, after we built ours, we compared like the performance of the Google bridge and our bridge, and we saw like the tail latencies for like the download speed for the two bridges. You could see that like ours shifted a lot. You could see like almost like a 4 point something X improvement for the P99. And so yeah, it massively, there's a big performance improvement from our bridge compared to the Google bridge. Primarily, there are like a bunch of optimization, but the primary thing was like working with fixing buffer sizes. The Google bridge was reading things in 8 KB segments, which is kind of like a limit from OKIO. And our bridge was able to like read in bigger buffer sizes. So, but there are like other optimizations too. And then we called our library OkCronut because merging the two names. And it's quite straightforward to work with. So you create like a single instance that's shared in the app process. And how am I doing on time? Okay. So we create this single instance. And then you use that instance to create like call factory. So as you can see, the call factory is actually OkHTP API. So you still like get to use the same APIs that you're familiar with, and it works with like retrofit and other things. But underneath, it would use Cronut or OkHTP, depending. I mean, there's a bunch of details here, but like the thing we try to do is that like while initializing Cronut, you have the options of like saying use Cronut versus use OkHTP. So this allowed us to like run A/B tests, for example, to figure out what is the impact of both. So yeah, it's quite straightforward to use, and a very simplified API surface, we think. And once this is done, the next thing is for the clients to know that your server supports this new protocol. We highly recommend using manual hint. So this is you saying, this is my server, and this is the port it's available on. And same iOS have something similar where you could turn that on, but like even if you don't manually add this hint, HTTP3 support is automatically detected, could be automatically detected using something called the HTTPS DNS resource record, which would tell the client while it's making a DNS query that this domain supports H3. And then there's also the other option of like HTTP3 alternative services where the backend sends a header saying it supports a H3. Okay, to the fun part, we ran an A/B test of H3 with Coronet and H2 with OkHttp, and this is gonna like share some of the impact of that test. So the first thing we noticed was a 51% improvement in connection times across the board. So you see that the markets where we used to have like long connection times, when we switched to H3, it got significantly better. Like everything went from like red big dots to like smaller. So it went from like like this is P95, and the connection times went from like being like 1 second or so in this market to about 500 milliseconds or so. So like this is kind of consistent with the idea of like reducing one round trip and having like one less work to do. In some market, the improvement was more significant, seeing like 60% or so improvement, whereas in others, we just saw like a marginal improvement, like if they were already good, like if the round trip time was like short previously. So connection time significantly improved. With the OkCronet library, we also see that like for our high priority requests, like the home screen request, we see that the request actually started about 4.4 times faster because we have like a dedicated thread pool for requests now compared to previously, where like it was kind of like at the dispatcher, and the dispatcher didn't have like any notion of priority. So it was kind of like treating like other auxiliary requests as important as the primary request. So we saw like improvement in the time to actually start the request from our bridge that we built, OkCronet. And finally, looking at the total response time at the moment, this is the improvement we're seeing. We see like a 14.5 percent improvement in P90, and about 17.9% improvement in P95 for our home request by making the switch, which for markets like Pakistan is like about 500 or so milliseconds, but this is like for all the markets that we operate in. Yeah, and there's still like some optimization we need to do on the OkCronet library, but we plan to open source it sometime in October. So if you want to also like use Cronet or also like get like similar improvement in your networking performance, be sure to check it out. I put like a QR code in case you want to like sign up for a form, and we'll just like message you there like, oh, the library is ready, and if you want to use it. But yeah, we plan on open sourcing it. There's still like some bug fixes and some cleanups that we need to do here and there, but plan to open source it next month. And yeah, that was it. You could reach out to me on my website, or also I added like a QR code for LinkedIn if you want to like reach out to me, speak about, I don't know, networking or anything in general. Yeah, I think I'm good on time, and I have time for questions.